All right, the next example, second derivative of y minus the first derivative of y plus y equals t, and the initial conditions are y0 is 1 and y prime of 0 is 1. Step 1 is to take the Laplace transform. Now the Laplace transform of y double prime is equal to s squared y minus s y0 minus s y prime of 0. The Laplace transform of minus y prime is minus s times y minus y of 0. And the Laplace transform of y is simply y. And the Laplace transform of t, so the Laplace transform, I'll write that one separately, is 1 over s squared. Now together we can rewrite this, so this is equal to 1 and that is equal to 1. So we get s squared times y minus s, sorry, there shouldn't be an s there, sorry, minus 1 minus s times y minus minus 1, so it's equal to plus 1 plus y equals 1 over s squared. And now so we've taken the Laplace transform, step 1 is complete, and now we want to isolate y. And we have s squared minus s plus 1 times y minus s minus 1, minus 1 plus 1, so these cancel out, is equal to 1 over s squared. Now almost there. So we get, so I'll move this minus s to the other side. So s squared minus s plus 1 times y is equal to s plus 1 over s to the power of 2. And to be able to divide this in a slightly more easy way, I will rewrite this as, let's see, s to the power of 3 plus 1 over s squared. And now I can rewrite this as y equals s to the power of 3 plus 1 over s squared times s squared minus s plus 1. And now we have completed step 2. Now the final step here is writing this in a form where we can apply the inverse Laplace transform. Let's see. Yep, okay. Now the book does something tricky here. It rewrites this in such a way that you can immediately write out the answer, but that requires that you are really familiar with this one, and this example was also designed for that trick, and we're just going to ignore that trick and imagine that we simply don't know what to do here. But what we do know is that, so s squared minus s plus 1 will have complex roots. So this is a quadratic factor. This is a repeated linear factor, s minus 0, but of course the 0 doesn't show up. So we can write y, well, this fraction we can write as a over s plus b over s squared. So this is the part of the repeated linear factor, plus cs plus d over s squared minus s plus 1. And now we are faced with finding the coefficients a, b, c, and d, so that if we put this back in with the common denominator of this, we can equate that to s to the power of 3 plus 1. So let's do that. So we want to rewrite this as a over s times s times s squared minus s plus 1. So this is the first factor, so that now it has the same denominator as the original one, plus b times s squared minus s plus 1 over s squared, and that same denominator, plus cs plus d times s squared, and now we have all the three fractions with the same denominator. Now, okay, this seems a lot, but let's clear this up. It turns out that if we, well, let's rewrite this. We get as plus b times s squared minus s plus 1 plus cs to the power of 3 plus ds squared over s squared times s squared minus s plus 1. And we finally rewrite this to a s to the power of 3. Of course, I've done this before. And this is just multiplying these things out. Plus bs squared minus bs plus b plus cs to the power of 3 plus ds squared divided over our denominator. And this has to be then equal to s to the power of 3 plus 1 over the same denominator. So what we get is, this should be a power of 3. We take all the powers of 3, 2, 1 and the constants together. So here we have as to the power of 3 and we have cs to the power of 3. So that is a plus c s to the power of 3 plus b minus a plus d s squared. So that is that term, and that term. Plus a minus b times s. So that is that term and that term. And we have one constant term plus b. That has to be equal to s to the power of 3 plus 1. So we get three equations. We get a plus c equals 1 here. We get b minus a plus d. Well, there's no s squared term here, so that has to be equal to 0. There is, we also know that a minus b has to be equal to 0, and that b is equal to 1. And luckily, because we have this one, we can calculate this fairly easily. If b is equal to 1, then it follows that a is equal to 1. And if a is equal to 1, then c must be equal to 0. And if a is equal to 1 and b is equal to 1, then d must be equal to 0. So we have that y is equal to 1 over s plus 1 over s squared, and that's it. Because c is equal to 0, d is equal to 0, and we're just left with this. Now, if we take the Laplace transform, the inverse Laplace transform of y, we get that the inverse Laplace transform of 1 over s is simply 1. The inverse Laplace transform of 1 over s squared is t. And that is the solution to our differential equation.